In this video, we will introduce our new work, revisiting rolling shutter bundle adjustment toward accurate and fast solution. CMOS cameras equipped with rolling shutters have been widely used in our daily life. Compared to global shutters, rolling shutters expose pixels row by row, with a constant time delay. Therefore, images captured by moving rolling shutter cameras will produce distortions known as the RS effect. Bundle adjustment is the problem of simultaneously refining the camera's pose and the observed point's coordinate by minimizing the reprojection errors over observed image points and 3D projection points. As demonstrated in many works, the 3D vision problem is sensitive to RS effect perturbations. Even a minor rolling shutter effect disturbance will cause a loss of structure and pose accuracy as shown in this slide. Compared to the standard global shutter bundle adjustment, rolling shutter bundle adjustment explicitly modeled the instantaneous motion parameters, which results in a more clean reconstruction and accurate poses. As solving RSBA is a challenging problem. In the last decade, many works have been proposed to address this issue. The first group of works solve it in a continuous paradigm which assumes a video input. We argue that this continuous image input assumption is not general enough for keyframe-based SLAM and SFM applications. On the contrary, the second group of works attempt to model the instantaneous motion model explicitly. Unfortunately, as proved in ECCV 2016, once the y-axis of the cameras is in one direction, there will exist a degeneracy configuration which will flatten the entire structure into a plane. Besides, although the explicitly modeled instantaneous motion parameters keep the original sparse characteristics in rolling shutter bundle adjustment iteration, none of the work has tried to accelerate the whole rolling shutter bundle adjustment. Based on the above motivations, we proposed a rolling shutter camera bundle adjustment called NW-RSBA, with unordered image input which leads to a degenerate-free, accurate and fast solution. The detailed contribution is listed as follows. To begin with, let's first review the rolling shutter motion formulation and rolling shutter bundle adjustment. We adopt the instantaneous motion model used in ECCV 2016, where the rotation and translation of each row are linearly dependent on the observed row index. Based on this, we can formulate the basic projection model from 3D space to the image plane. We further formulate the whole rolling shutter bundle adjustment problem. Compared to the global shutter, for each camera, we have two more parameters to optimize. In this slide, we list three existing RSBA methods. Direct measurement-based RSBA uses an observed image point row index in the projection function, while normalized measurement-based RSBA uses a normalized image point row index. Compared with modeling rotation and translation based on observation, the direct camera-based RSBA utilize the rolling shutter constraint to get the closed-form solution of RS projection which is free of observation. In our work, we first analyze the accuracy improvement using normalized image points. We believe that the improvement comes from the more precise instantaneous motion approximation of low-order Taylor expansion when conducting normalized-based bundle adjustment. We also provide a small experiment on the left which directly proves our idea. The green star represents the ground truth solution, and the red star represents the local minimal point in the reprojection error surface. This shows that non-normalization solutions always have a biased solution. And another small experiment on the right demonstrates that choosing the middle row as the start point will result in a more accurate result. This can also be qualitatively viewed in the middle figure. Compared with the non-normalized method, our rotation representation is more close to real rotation. Secondly, we propose a weighting technique. We argue that this technique can enhance optimization stability and prevent degeneracy. We explicitly model the covariance formulation of reprojection error through noise propagation from prior observation Gaussian noise. As shown below, with the reweighting technique, we can reshape the reprojection error covariance to isotropic. As proved in ECCV 2016, under the planar degeneracy configuration, the y component of the reprojection error will reduce to 0, which denotes that the covariance matrix holds a 0 element in the y direction as we show in the left. Our method have explicitly modeled the error covariance and standardized it to isotropy. Thus, the proposed method exponentially amplifies the error during the degeneracy process, which will prevent the continuation of the decline from ground truth to the degenerated solution as shown in the right figure. This technology empowers the degeneracy resilience ability to our bundle adjustment. We also carry out a qualitative experiment. With the same initialization configuration, GSBA only recovers the unclear structure. NM-RSBA fails to the degeneracy solution. NW-RSBA has the most accurate reconstruction results. Finally, we propose an acceleration algorithm. In most scenes, the number of 3D points is much larger than the number of cameras, and solving the normal equations consumes most of the time. Since this involves solving a system of high-dimensional equations. Previous work used Schur complement to iteratively solve for cameras and 3D points, and this approach inspired us. We first separate two instantaneous motion parameters with original camera pose parameters, which leads out the parallel connection structured Hessian matrices as shown in the right figure. Its sparsity character can be used to further accelerate the normal equation. Therefore, we extend the Schur complement technique to the two-stage Schur complement. The algorithm is summarized in the left. We carry out a synthetic experiment to verify our acceleration strategy. As the camera number rises, the proposed method achieves an order of magnitude faster than the baseline method. In the experiment, we first test our method in a synthetic environment. We simulate 5 RS cameras located randomly on a sphere pointing at a cubical scene as shown in the right. We compare all methods by varying the speed, the image noise, and the readout direction. The results are obtained after collecting the errors over 300 trials per epoch. We measure the reconstruction errors and pose errors. As shown in this slide, our method achieves the best accuracy in all scenes. We also test our method with the real data. We augment RSSLAM by replacing the local BA and full BA modules with NW-RSBA. We compare all the RSBA methods in publicly available RS datasets TUM-RSVI and WHU-RSVI dataset. We use two evaluation metrics, namely 8, absolute trajectory error, and tracking duration DUR, the ratio of the successfully tracked frames out of the total frames. The table below demonstrates that our method achieves the best accuracy in most sequences. Besides, our method is more stable than other methods. We also illustrate 4 trajectories estimation compared with the ground truth, which further confirm our statement. We visualize our reconstruction comparison in sequence 3 TUM-RSVI dataset. Our reconstruction is more clear and close to global shutter reconstruction. We augment visual SFM by shifting the incremental GSBA pipeline with a proposed NW-RSBA. We test our proposed method on 2 self-made datasets and compare the quantitative accuracy against the GSBA and the NM-RSBA. Our proposed NW-RSBA works better in motion and 3D scene estimation while GSBA obtains a deformed reconstruction. Specifically, the sparse 3D reconstructions and recovered trajectories of NW-RSBA look much cleaner and smoother than the ones from GSBA. NM-RSBA reconstructs 3D scenes which collapse into a plane since the datasets contain only one readout direction. In contrast, NRSBA provides correct reconstructions. The results also verify that error covariance weighting can handle the planar degeneracy. Thanks for watching.